guys pay a little bit of attention, but you don't get the broad strokes sometimes. So today I want to talk to you about some of the broad strokes that might be able to pull a few threads together. We'll see. I want to start with a standard capacitance circuit, something that we would and have studied a lot already. So a straightforward RC circuit. This is not a big ask, but if I were to close the switch and ask you guys to use Kirchhoff's laws to prove the time how long it would take for the capacitor to reach half of its charge, could you guys run the derivation for that? Could you come up with the expression that would show the rate at which the capacitor would charge? That'd be setting up a Kirchhoff's loop, from there creating a differential equation, and then solving that differential equation to get Q as a function of time. Is that something you can do? And I don't know if you can or not. You haven't seen this particular example since November, but let's start the class off with just 3 minutes. If you can do it in 3 minutes, great. If you can't, get as far as you can. And I don't care whether you give me Q as a function of T, or well, maybe not that. Maybe I'd write this as V over C as a function of time, or V over R as a function of time, or I as a function of time. Can you give me any of these? You're supposed to be able to. We'll assume that the capacitor is uncharged at time equals 0. What can you give me? Now that we've taken a moment to go through and determine a relationship that would fit the current or the charge on the capacitor, I want to speak about the current on the capacitor. There's no current passing through the capacitor. In fact, I think all of you know that without much discussion, that there's no current ever passing through a capacitor unless the capacitor has failed. This brings us to a problem, at least a problem that was put forth by Ernest Maxwell, and looking at, and not just him, there are others who propose this problem. But the issue comes down to how does Ampere's law actually behave? Ampere's law tells us that there must be a magnetic field around the outside of the wire as long as there is a current passing through the wire. Now, we have a current that's going to decay, and I've made a mistake, and nobody has seen it yet. Would anybody like to tell me my mistake? Because it just occurred to me I made a mistake. Okay, well, which allows us to make the correction over here because we screwed up earlier. And remember that we need to take the derivative, and that gives us e to the negative t over rc. All right. So I close the switch at time 0. At time 0, Ohm's law prevails, and we get a current that is determined by the size of the resistance. We know other facts about this, that the current will decay faster if the resistance is smaller. The current will stay there longer if the resistance is bigger, because the resistor is kind of determining how fast the charges can move through the circuit. C also plays a role in there, because if C is bigger, it can hold more charges. So we have more charge to work with. All that is what we're playing with here. But we also know that after a long period of time, the current's going to be 0. So let's start with the idea that this circuit produces a changing current. And I want you to tuck that into your back of your mind, because we've talked about what a changing current can do. In fact, I want you to think very cleanly. If the current were passing in this direction, at time 0, when that switch is first thrown, isn't there a magnetic field directed in either out of the page or into the page? Which direction would that magnetic field be the moment the switch is closed? Well, one would hope. How many of you say into the page? How many of you say out of the page? This magnetic field is impingent on a closed loop of current, correct? So there is a magnetic flux here. There was an instantaneous change to the current, right? I closed the switch, and instantaneously there was a current that was developed. That made a change in flux in the loop. Tuck away in your mind that had to cause an EMF in the loop. I'm not talking about this EMF. I'm saying that somewhere in this entire circuit, in this whole loop, an EMF was generated to try and prevent the change in flux, which means throughout all the wires that were there, there had to be an EMF in this direction caused by the change in flux. This is what Faraday's law says. This mere closing of the switch creates an EMF due to the rate of change of the flux. There's a huge spike in current, therefore a huge spike in flux. This is called the back EMF. And occurs in every circuit, because every circuit is a closed loop. Every time you flip a switch in a circuit and you generate a current, you are generating a changing magnetic flux. It might not be much, but it's going to be there. In fact, a clever person realized you could probably harness this back EMF. Back EMF is going to be the start of something known as inductors. Tuck that away for tomorrow. Something else is happening here. But tuck that away for tomorrow. We close the switch. At time equals 0, there's an instantaneous current. It's equal to this. And as we just described, that means there's going to be a magnetic field around the wire. In fact, if I take my Amperian loop and put my Amperian loop around this wire, we could talk very cleanly about what the size of that magnetic field would be. We've done that job before. That's Ampere's law. And so you're aware of how Ampere's law is supposed to work. We know that it has to do with the current enclosed. And that has to equal a integration that sums up the entire magnetic field around a loop of wire. The thing about Ampere's law that's a little bit funky is it doesn't specify the plane that has to be broken by the current. I know you're having a hard time with those words because I had a very hard time hearing them the first time, and I've been able to roll this over in my head a lot. But I want you to imagine that this Amperian loop that we've drawn right here, imagine that it's like a butterfly net. So it has a very long connection behind it. That butterfly net represents the plane that the current has to go through. So we've assumed that when you have a Amperian loop, the current enclosed passes through a plane created by that loop. A plane is just the part that would connect the loop together. Like our loop is a loop, and there's a plane across it, and the current has to puncture through or pass through that loop. You follow what I'm saying? Okay. So what I mean is, but what if that plane was actually like behind it a little bit? It would still capture that current. So you see what I mean by like a butterfly net? It'd have that casing behind it. What if I say my Amperian loop is here? And the plane, or the butterfly net portion, passes through where the capacitor is. Is there any current enclosed in the loop? No. But will there be a magnetic field detected at the location where my Amperian loop is? That was the question posed by Maxwell in trying to study this. Ampere's law is a law. It should work in all circumstances. And the real question is, do we assume that in Ampere's law, you have to make it a two-dimensional loop, so you can't have this quandary? Or do we assume that, well, if it's maybe the law doesn't work in all circumstances, therefore it's no longer a law, it's more like a suggestion? Because there's a reverse of this too, meaning there is the possibility that we have our Amperian loop where the capacitor is, but that we pass the butterfly net portion where we know the current is puncturing. The question now is, would there be a magnetic field detected between the plates of the capacitor? We have an enclosed current, but our Amperian loop is totally contained inside the space between the capacitor. An idea was submitted that perhaps there is a magnetic field in the location between the plates, and that Ampere's law, in order to be a law, would have to be invariant regardless of where your butterfly portion went. It was proposed to add something to the function, something to ensure that the right side always showed a magnetic field, but that the left side could be conceivably convinced that it wasn't always a current that caused a magnetic field. And I know that I'm not making this perfectly clear, but let's just kind of zoom in for a moment on the capacitor plates themselves. So imagine we're just looking at the capacitor plates themselves. At time equals 0, what's the charge on the plates? 0. What's the electric field between the plates at time equals 0? 0. The first electron makes its way, so we start getting a buildup of charge on the plates. Although I think, based on the way I drew it, it would be plus on this side and minus on this side. So the beginning hints of an electric field begin to develop between the plates. And then the next electron is deposited, and an electric field gets stronger between the plates. As the current pushes charges, the electric field goes from being 0 to some maximum value. In fact, because it's a capacitor, and we're talking a parallel plate capacitor at that, we know that the voltage across the capacitor has to equal the electric field times the distance between the plates. Meaning our electric field could be described with the same effective relationship that we have for the electric potential. That the electric potential is going to build up until it reaches some maximum. So there is a changing electric field inside the area between the plates. The belief is that this changing electric field acts like a current and produces a magnetic field. This is called the displacement current. It's not a current, and it's a stupid name. They shouldn't have named it that. In fact, in retrospect, the belief was there was something else happening because they didn't fully understand what was happening with circuits. So the name stuck, and we still call it the displacement current. But the displacement current is about the change in electric flux between the plates. The rate that the electric flux changes determines the size of the magnetic field between the plates. It's an additional term that has to be added to Ampere's law to account for the fact that a magnetic field isn't just caused because of a current, but a magnetic field can also be caused because of a changing electric flux. mu naught epsilon naught times d flux dt. This portion is called the displacement current. Either one of these can generate a magnetic field. In fact, the magnetic field inside the plates of the capacitor is effectively the same as that of the current on the outside. But what this also means is that anytime an electric field changes, a magnetic field is generated in that place, as if there was a current there. To me, that's already a little bit weird and speaks to that maybe there's something more going on with electric fields and magnetic fields than what the original ideas have led us to believe. But this isn't all. This is just a start. Okay, I want to add something to this. But for the time being, how about I just give you a few moments to make sure you have this in your notes. Or I guess I don't really care if you have this in your notes. I'll put the bars on there. And you guys can take care of your notes. But it's called the displacement. I just want you to let it sink in for a second. But I also want to consider something else. So, we good for me to move on for something else? This magnetic field is circular because of the direction of the change of the electric field. The weirdest. If you look it up in your equation sheet, you'll find that the technical definition of an EMF is to integrate the electric field between 2 points. That's what we did last semester, if you'll recall. And although I may not have used ds, I may have used dx, the issue is that if you integrate from one place to another, the electric field, you get the change in potential. So whether I use this symbol or I use change in potential, at this point they're interchangeable. This is the definition of voltage. For the parallel plate capacitor that we just used, we used that with the idea being that the electric field was uniform between the plates. And so if integrating a constant, we just get the integration of the integrand. Well, EMF also equals negative n times the rate of change of the magnetic flux. Faraday's law, correct? Let's scrape away the number of loops for just a minute to not make it more complicated looking than it has to be. If I have a loop of wire, welcome. If we have a loop of wire and there's a magnetic field all around it, on the surface nothing happens. When the bar was being pushed through the magnetic field, we could use the right-hand rule to tangibly discuss the push on those charged particles towards one end of the bar. Did that feel tangible to you? We'd played with magnets. We knew what we were talking about. We had seen things already at that point related to lab. It felt like, yeah, that seems plausible, that if that were happening, our charges would experience that force because they had a velocity to the magnetic field. This feels less tangible to me. That suddenly we just start losing a magnetic field, and let's just say the magnetic field is decaying, which would mean I would have to create a current that would try to oppose the change or the loss of magnetic field, which would mean I'd have to get a current that is in this direction by using my right-hand rule. So B is decreasing. That generates a current. I've often asked myself, what's pushing on the charges? Right? What is causing those charges to move because the magnetic field is just changing? Faraday's law works. I know it works. We've done labs. I've dropped the magnets through the tube. We saw a little spike in the EMF. We know it does. But the real question is, what's pushing on the charges? It has been suggested that this changing magnetic field deliberately applies an electric field to the charges themselves inside the wire. In fact, all it would take is putting these things together to say that inside our loop, there would have to be an electric field due to the rate of change of magnetic flux. Just bring these things together. So the real question is, do I need the loop there at all? If there's no wire there, and I just lower the magnetic field, do I get an electric field? And believe it or not, the answer is yes. An electric field will be created in space. And it will be in the direction where a current would be in that same space. You see, what we found out is that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They both obey the same promises that we talked about. This electric field is circular because of the direction of the change of the magnetic field. If you put both of these together in your mind, if the magnetic field is changing, it's creating an electric field. And if the electric field is changing, it's creating a magnetic field. These two things should clearly feed into each other. As the magnetic field changes, the creation of this electric field is creating an electric field that is changing, which would therefore be creating a magnetic field that is also changing. Maxwell took this together and took both of these ideas and placed them together. He took the idea of a current not being there and just left it. He said, okay, no current. Let's just take the displacement. Just consider the changing electric field and just consider the changing magnetic field. He put these two things together and tried to apply the concept of a wave equation to this. If you look closely, you'll notice that we have two derivatives based on an integral sum, but it ends up being a second derivative based on our integral sum. If you work out a wave equation from this, you get a wave that propagates at a speed controlled by mu naught and epsilon naught. This value comes out to be 3 times 10 to the 8th meters per second, which is the speed of light. Although there's no current here and there's no capacitor, the changing fields will oscillate on their own. These oscillating fields propagate from a source, something that was a moving charge at one time. So basically you move electrons back and forth inside a wire, they generate a propagating electric-magnetic field. Maxwell's idea was that this was the foundations for light. He didn't know that it was light at the time. He just knew it was the foundations for an electromagnetic wave. And that's